So welcome you to this module. So in the last module, we discussed the affine invariant estimation of mu. In a module before that, we considered affine invariant estimation of sigma to power r. We already did a few examples for affine invariant estimator of sigma to power r. Now let me give one example which deals with affine invariant estimation of mu. So let us consider the following example. So what you have is x1, x2, xn are IID uniform, let us say mu minus sigma to mu plus sigma, where my parameter of interest is theta mu sigma, which belongs to r cross 0 to infinity. Let me take this as a parameter. So first I need to see whether this belongs to a location scale family or not. So I need to look at what is my f theta x1, x2, xn. So in this case, f theta of x1, x2, xn, because it is independent, so it will be a product of distribution functions of x1, x2, xn. So let me write down this as product I is equal to 1 to n. Because they are IID, so this common distribution function is not going to depend on I, so it would be only g theta of x1, x2, sorry, g theta of xi, because they all have the same distributions and they are independent, so it will be same as g theta of xi. I need to tell what my g theta x is. G theta x is the distribution function of uniform minus sigma to mu plus sigma. So certainly for x less than mu minus sigma, it would be 0. For x between mu minus sigma to mu plus sigma, this would be nothing but I integrate from mu minus sigma to x. So it becomes x minus mu minus sigma by total density. So let me make it sigma by 2 and sigma by 2, so that in the denominator I just only get sigma divided by sigma, because uniform PDF is 1 upon sigma in this case, 1 upon b minus a, and it will be 1 if x is greater than or equal to mu plus sigma. So this can always be written as 0 if x minus mu by sigma is less than minus 1, if x minus mu by sigma is greater than or equal to minus 1, less than 1, then how much is this? X minus mu by sigma plus 1, and this is 1 if x is greater than or equal to, or x minus mu by sigma is greater than or equal to 1. So you can see this all depends on mu and sigma only through x minus mu by sigma. So I can write down this as h of x minus mu by sigma, where what is my hx? Hx is 0 if x is less than minus 1, x is greater than or equal to minus 1, less than 1, it is x plus 1, and if it is x is greater than or equal to 1, is there some problem over here? Let me just check. This would be x less than minus mu by sigma by 2. So everywhere, because I have made it sigma by 2, it's greater than or equal to mu by sigma. So that makes x minus mu by sigma by is less than minus half. This is minus half to half. This is greater than half. Yeah. So it would be x between minus half to half. Am I making somewhere some mistake? What should be? Let us look at, because I have changed it mu minus sigma by 2 and mu plus sigma by 2. So then it becomes x minus mu minus sigma by 2 divided by the PDF b minus a, B minus A is nothing but mu plus sigma by 2, mu gets cancelled, so this is okay. Similarly, so this is okay, and this is okay. So this is same as x minus mu by sigma plus 1 by 2. And this is would be this, so this would be x plus 1 by 2. And this is 1 if x greater than or equal to 1. So what you see is f theta x for next to xn turns out to be product I is equal to 1 to n h of xi minus mu by sigma. So what you see is your joint PDF is of the type f of x1 minus mu by sigma, f of x2 minus mu by sigma, f of xn minus mu by sigma. So it belongs to the affine family. So my problem of estimation, so I consider estimation of mu. First I consider under square error loss L theta A, which is A minus mu whole square by sigma square. So what I need to know, now I know that my problem is invariant under G. So problem is invariant under affine group of transformations. So I have to find the minimum risk invariant estimator of mu. So what I need to do? First I need to identify one affine invariant estimator of mu and an affine invariant estimator of sigma. So mu is the location, so it looks like delta naught x. Now in this case complete sufficient statistic because of mu minus sigma by 2 and mu plus sigma by 2, there are two parameters. So complete sufficient statistic would be minimum and maximum. And mu is, I can take the average of the minimum and maximum, so I can take delta naught x to be x1 plus xn by 2, because mu is the average of these two. Mu is the average of these two endpoints. When you have a large sample, your minimum is going to be here and maximum is going to be here. So intuitively it looks like the average of minimum and maximum should be a reasonable estimator of mu. The only thing now I need to look at whether it is location invariant, affine invariant estimator of mu or not. To see whether it is a affine invariant estimator of mu, what I have to see? Delta naught of bx1 plus c, bxn plus c should be same as b times delta naught of x1, x2, xn plus c. So delta naught of b of x1 plus c, b of xn plus c. This would be how much? It was minimum of all the arguments. So here it would be minimum of bx1 plus c, bxn plus c. C is constant, so it will become minimum of bx1, bx2, bxn plus c. But b is positive. So minimum of bx1, bx2, bxn will become b times minimum of x1, x2, xn. So that means this will become bx1 plus c. So when you apply bx1 plus c, bxn plus c on x1, you get bx1 plus c. By the same logic, xn would get transformed to bxn plus c under this transformation because c is common. So maximum of these would be maximum of bx1, bxn plus c. But b is positive, so that is would be same as b times maximum of x1, x2, xn plus c divided by 2. And how much is that? So this is same as b times x1 plus xn by 2 plus c. 2c by 2 gives me c. So this is same as b times delta naught x plus c. And that is the definition of any invariant estimator of mu, affine invariant estimator of mu. So this implies that delta naught is an affine invariant estimator of mu. Now I try to look at what is the estimate of sigma. Intuitively, if you look over here, sigma is nothing but a range, population range. So it looks like I should consider the sample range as a estimator of sigma. So I consider delta 1x as xn minus x1, just this much. Now what I need to see is whether delta 1 satisfies the property of affine invariant estimator of sigma, which is equivalent to saying that whether delta 1 of bx1 plus c, bxn plus c is same as b times delta of x1, x2, xn plus c or not. So let us see that. So delta naught of delta 1 of bx1 plus c, bxn plus c. How much is that? Xn I have seen under bx1 plus c, bxn plus c would get transformed to bxn plus c. Similarly, the minimum would get transformed to b times minimum plus c because b is positive. So this becomes b times xn minus x1, but xn minus x1 was nothing but delta naught. So this implies that same as b times. What does that mean? This implies that delta 1 is an invariant estimator of sigma, affine invariant estimator of sigma. So what is MRE? Now note that in this case, delta naught, delta 1 are functions of complete sufficient statistic. In this case, because there are two parameters, mu minus sigma by 2 and mu plus sigma by 2, so complete sufficient statistic is x1, xn. So what it means is that minimizing u star w does not depend on w, and in fact that conditional expectation does not depend on w. So what is the minimizing u star? So the MRE is delta star x, which is delta naught x, minus u star times delta 1x. Now why u star is not depending on w? Because in this case w is ancillary and delta naught and delta 1 are functions of complete sufficient statistic. So the minimizing u star is not going to depend on w. So in fact what I know is, I exactly know what is the form of u star. My u star for the squared error loss function is E01, that means when mu is 0 and sigma is 1, of delta naught x, delta 1x, divided by E01 of delta 1 squared x, which is same as delta naught x is nothing but xn plus x1 by 2. Delta 1x is xn minus x1 by 2. So it becomes 1 by 2 xn square minus x1 square divided by E01. Delta 1x is nothing but xn minus x1. So this is what it is. So you need to calculate this. I'll try to use some trick over here. So note that under mu sigma, which is 0, 1, that is where you have to calculate this expectation. x1, x2, xn are IID uniform minus half to plus half. Mu is 0 and sigma is 1. And uniform minus half, half is symmetric about 0. So that means x1, x2, xn has the same distribution as minus x1, minus x2, minus xn. Because if you consider x1 as minus x1, the density is half only. If x was between minus half to half, minus x is also between minus half to half. So your PDF remains invariant. And because they are independent, their joint PDF is same as product of marginals, and product of marginal of xi is same as product of marginal of minus xi. So that means distribution of x1, x2, xn remains same as minus x1, x2, xn. I'm trying to get the relationship between x1, x2, xn this, I'm trying to get relationship between expected value of xn square and expected value of, so what does that mean? That means I take the joint distribution here as minimum and maximum. So minimum maximum would be x1 and xn. Has the same distribution as, I apply the same function over here. That means the first coordinate as minimum. Now minimum of minus x1 minus x2 minus xn is same as minus of maximum x1 x2 xn. So this would have the same as minus xn. And second coordinate here is xn, which is maximum. Now maximum of minus x1 minus x2 minus xn is same as minimum of x1 x2 xn minus of. So what do you get from here? In fact, it says x1 has the same distribution as minus xn. So this implies that x1 has the same distribution as minus xn. So expected value of x1 square is same as expected value under 0, 1 minus xn whole square, which is E01 of Exn square. Movements exist because range of uniform is finite. So what do you get? U star is 0. So MRI of mu under a affine group of transformation is nothing but only x1 plus xn by 2, because that U star turns out to be 0. A natural question to ask is, can I generalize this result to more general loss function? So now let us try to consider a general loss function. So far we considered only square layer loss function. Let us consider general loss function. So what I do is I consider L theta A to be W of A minus mu by sigma whole square. I assume that W possesses the properties of square layer loss function. So W2 is equal to T square has a property that it is even. So W of minus T should be same as W of T. Second thing is W is convex, because Wt is equal to T square is convex. So let us assume these two properties. Can I say that still this estimator is x1 plus xn by 2, which will tell that this estimator is quite robust in the sense that it is not only MRE for square layer loss function, but it is also MRE for very general class of loss functions of the following type. So let us see that. So what I need to see is whether minimizer U star W is 0 or not. Now in this case, minimizer U star does not depend on W, because that conditional expectation, because of Basu's theorem, does not depend on W. So my U star minimizes this quantity, E01, 1, W of delta naught x minus U times delta 1x under mu is equal to 0 and. Now what I will prove is psi of U is same as psi of minus U. That is the first thing I will use. So I'll try to prove that psi of U is same as psi of minus U, and then anyway this is a convex function of U, because W is a convex function of U. You can take the double derivative. It will be W prime delta naught minus U delta 1x. Assuming that derivative I can take inside the expectation sign, then delta 1x with a minus sign. When you take the double derivative, here delta 1 square will come and W prime of all that, so which is always non-negative. So this is clearly a convex function of U. Second thing, I'll try to prove that psi of U is same as psi of minus U. For that, note that I have shown that x1 xn has same distribution as minus xn minus x1. So under mu is equal to 0 and sigma is equal to 1, x1 xn has the same distribution as minus xn minus x1. So what does that mean? Delta naught x, delta 1x, which is nothing but x1 plus xn by 2, and xn minus x1 by 2 has the same distribution as x1 has same distribution as minus xn. So I replace here the tuple x1 xn by minus xn and minus x1. So when x1 xn is replaced, so x1 I replace by minus xn minus x1 by 2 minus x1 plus xn by 2. So what does that become? That becomes, yeah, minus of x1 plus xn by 2, so minus of delta naught x, and this is delta 1x itself. So what does that mean? Expected value of w of delta naught x minus u times delta 1x. I can replace delta naught by minus delta naught and delta 1 by delta 1 itself. So that means my psi of u would be same as E01 w of. So delta naught I can replace by minus delta naught minus u times delta 1 x, right? Because delta naught delta 1 I replace by minus delta and minus delta 1 because they have the same distribution. But my wt is same as w of minus t. So this is same as E01 w of delta naught x plus u times delta 1x, because w of minus t is same as w of t. But what is this? This is exactly same as this, except that u is getting replaced by minus u. So this is same as psi of minus u. So psi is convex, psi of u is same as psi of minus u. So the minimum would be attained at u is equal to 0, which we have done many times. I can do it. So psi 0 is same as psi of u plus minus u by 2 for any u. Psi is convex. So this would always be less than or equal to half times psi of u plus half times psi of minus u. But psi of u is same as psi of minus u, so this is same as psi of u for every u. So this implies that u star has to be 0. That means psi at value 0 is smaller than psi at any other value u. So what does that mean? That means MRI is again delta naught. Because u star is turning out to be 0. So what we saw in this case is x1 plus xn by 2, which initially we obtained the best affine invariant estimator under a square error loss function. We saw that in fact it remains best affine invariant estimator under any loss function which is even convex. So what I'll do in the next module is I'll take up possibly a couple of more examples dealing with affine invariant estimation. So thank you very much for your patience.